Hi, welcome back to CM4269, and this is the second part of the Catalyst lecture. Okay, so here we are. We are still in heterogeneous catalysts, and we've tackled zeolites, and we're now going to think about some of the other heterogeneous catalysts, and then we'll make our way through single site catalysts and then proceed through the rest of the program. Okay, oops, where are we going? There, I hope. Okay, oxidation catalysts. Now, you know without me telling you, oxidation is a key process, particularly hydrocarbons. Using air is good, or hydrogen peroxide. Both of these are quite green examples. And here is an example of a catalyst which you might think at first glance, oh look, there's another zeolite. But no, it's a catalyst called TS1, and it's actually a metal catalyst, so that effectively take the ZMS5 structure and replace all the aluminium by titanium, and you end up with this. It's a more rigid structure, but it's really, really good at catalyzing oxidation, particularly with hydrogen peroxide, because hydrogen peroxide is really quite an unstable substance in the presence of certain metals. And basically what this catalyst does is it produces sites so that the hydrogen peroxide destabilizes and then affects the various oxidations. For instance, like this. This is just a little example of some of the flexibility of using hydrogen peroxide and TS1. TS1, widely used, very useful catalyst. Okay, I'll let you read this. Effectively, this whole group of titanium substituted zeolites, so they're no longer zeolites. Lots and lots of applications, and I'll just let you read that. Again, we've got a long lecture, so I'm not going to wait around very much, because you can always pause this and read it and then carry on or look at the slides. Okay, so how do catalysts work to effect shape selectivity? Well, you've already seen with zeolites, effectively molecular sieving or the like. If you organise active sites in the right places in the structure, you can use transition state theory or steric hindrance of intermediates, again to move products sterically where you want them to be moved. Or you can use, in inverted commas, solvent concentration. So an example here, certainly of A, would be slide 22 on toluene. For B, this is a good example. Xylene isomerization without disproportionation over hexamers S5. You can't ever quite get rid of zeolites, they're everywhere, but effectively transition state theory of intermediates is being used to actually get the particular isomer that you wish. Third way, this concentration of reactant molecules. It's higher, or solvent molecules, it's higher in the micropores than in the gas phase. Hence, you can increase the rate. Okay, moving away from the metal catalysts, I'm not too far away, but a little bit away. Let's think of heterogeneous base catalysis. Now, homogeneous catalysis, base catalysis works very well, has lots of advantages, but of course generates waste and reagent loss. So there have been a number of examples to try to capture some of the examples of homogeneous base catalysis pardon me, in a heterogeneous context. So typically metals, metal oxides impregnated onto aluminum or silica or ion exchange zeolites always keep coming up, are often used. We'll look at a case study in the biodiesel case study of using sodium aluminate. Gives you a 90% conversion, and aluminate is really the amphoteric oxyanion Al2O-. So we'll deal with the detail of that later. But let's now look at another similar idea where typically trying to use base catalysts in a heterogeneous context. Well, theoretically, if I could get this to work. Here we go. Okay, aminopropylsilane. So what we have here is you can see that you have effectively a silica base, and you silanize it. Salinization is a major technique used in things like gas chromatography to deactivate glass surfaces so that they don't interact with your analytes as they're trying to go through the chromatograph. However, in this case, you can actually put these extended bases onto the silica base. So extended base as in alkali catalysts onto the silica base. And the results are really quite astounding. So, using this type of system, you're able to do Michael additions and Nova-Nagel reactions with a heterogeneous catalyst, base catalyst. Spectacular. I know you know these reactions already, so I won't wander through the mechanism. Okay, so we talked about silica and salinizing silica just so the silica is a support. The other way of doing this, the other base that's often used, is polystyrene. Doesn't have a particularly well-defined structure, but does swell in solvents, so it provides a very high and accessible surface area which you can carry out reactions on. So effectively, one way of doing it is to put specific amounts and fractions of various functional groups, like as you can see here, and then these can be reacted to give particular catalytic properties, both acids and base catalysts actually. Okay. Or you can go for bespoke oxidation catalysts. Nicotinic acid at greater than 400 centigrade, conversion 50 degrees centigrade, conversion 50% to start with. The degasser process has actually not got better than 95%, but typically you're using a bespoke catalyst like this vanadium pentoxide, titanium oxide, oxygen type system. How did you get there? Unfortunately, it was just trial and error. The original method started up here. Right, okay, let's have a look at other types of heterogeneous catalysts or supported catalysts in the same way with the base catalysts, heterogeneous base catalysts and heterogeneous acid catalysts actually. You can support other types of catalysts using various bases. Now in this case the supported catalyst is a peruthenate, and you're using zeolite X to support the catalyst, so the zeolite framework is giving you the shape, if you want, the structure, the shape selection. You can equally put this type of catalyst onto a functionalized polystyrene base, but you get loss of activity, which tells you something, that the zeolite as a support, yes, it's giving you shape, but it's also organizing the geography, the geomorphology of the active sites in a way which is conducive to the reaction. You get loss of activity because you get the Hoffman reaction, which actually loses you what you're looking for. If you put it on unmodified hydrophilic silica, poor reactivity. On mesoporous silica, MCM41, stable and active. So, and the reason for that, well, it's thought to be transport of oxygen. The point of this slide is that you can have a chemistry, but not chirality, the steric influences of structure are important, and also the support itself is often not simply being an inert support. It's actually taking part in the reaction, either making it happen or not, as the case may be. Okay, let's move on next to, again, another continuing with the idea of getting some of the homogeneous properties into heterogeneous. Let's think about Lewis acids. Again, homogeneous is always good, but the same old problems. Wouldn't it be lovely to be able to have a sensible candidate for the acylation of unactivated aromatics, i.e. the Lewis acid type system? Okay, so if we think about clays, zeolites, the polyacids, then maybe there might be a way to go here. Now, whilst there have been certain types of successes with this, small molecules particularly, and you can use fixed bed reactors and no solvents if you're using the bed, the zeolite effectively as the Lewis acid. There has not been, amongst any of these potentially good candidates, a general acylation type catalyst. However, here are a couple of the examples which not general but specific, mostly small molecules, but useful. Whether there's a general way ahead here is more difficult to know. At the moment, I don't know of anything which is a candidate as a general catalyst. If we go on to clasic, that's an acid-treated clay containing zinc chloride, again the Lewis acid, or zinc 2 on MSM6, then again you can get this class of reaction. So effectively you're getting a heterogeneous Lewis acid. The future is probably triflates, lanthanum triflates, and we're going to talk about those in a couple of minutes. Okay, let's move on. The next major class of catalysts are the single site heterogeneous catalysts, so-called SSHCs. Now, these catalysts basically have active centres distributed uniformly over the surface, but they're isolated from each other. So the expression is usually crosstalk when you get active sites which are close enough to each other that you can have interaction between them. In these cases, that's not how it works. Usually the active sites are tethered to the surface, a bit like hydrogen in zeolites. So this is a little artist's impression of a type of thing we're talking about. They look distinctly like eyeballs, which is not helpful. So these are single pendant rhodium and platinum-based catalysts attached to alkane thiolate or alkane functionalized chains to low area gold or silicon chips, and the reference for this is given below. So you've got a nice flat surface, and effectively you've got these active sites, metal sites, sticking up on these tethered daisy-like things. I won't call them eyeballs, that's just not very nice. Okay, let's now look at this a bit more closely. So here are some examples where you have metal organic supported complexed catalytic metal. Here we've got palladium, here we've got rhodium, and then it's getting more and more like vitamins, isn't it? Where you then have oxidations catalyzed by the complex metal ions, and of course you're looking at the d electrons being involved here, and we'll talk a bit more about that later. And equally, here's one example on a silicon wafer, here's another on a gold surface. Okay, so these SSHCs, an awful lot of potential, very organized is not quite the right word, but very uniform. Let's actually have a look at those surfaces a bit more closely. So, the left here is a high resolution EM photograph of again a zeolite acid catalyst, which shows you again the surface structure. The SSHC here is actually a model of a structure showing the Bronsted acid sites, loosely attached hydrogen atoms to the aluminium frame. So in one sense, this model, mathematical molecular model, at least looks quite a lot like the reality, and this zeolite actually is acting as a SSHC with separated active sites. And some more examples of aluminosilicates with different metals, but again acting as single site SSHCs, because the active sites are separate from each other, so there's no crosstalk, there's no interaction between the active sites, whether you're talking about zeolites with their hydrogen ions, or whether you're talking about much more functionalized and customized types of system. Okay, I'm going to move on now away from SSHCs. We are just going to summarize. An SSHC is defined as active centers spatially isolated from each other and distributed uniformly over the surface. Here are some of the very facile conversions that you can effect using SSHCs, inorganic SSHCs, and you don't use any solvents. If you're using the more organic SSHCs that we talked about, where you're using the metal as the active site, you can do some even more interesting conversions. Okay, so now we think about biocatalysts rather than either things that we've made or more, I wouldn't say naturally occurring SSHCs, but SSHCs that actually function in that way almost on things like zeolites. Now, there's fundamental differences between the active sites on a metal or metal oxide surface and those on a nanoporous solid. We've already just talked about when you separate active sites, you don't get this crosstalk, you don't get interaction. But on a metal oxide surface, they absolutely can and do interact. Now, that type of separation of active sites begins to feel quite familiar, because enzymes, which are just biological catalysts after all, they use spatial separation with active sites so that they can affect their translations, they can affect their reactions just by either moving the molecule round to line up the active site, or as the molecule moves through a reaction path, then it encounters various reaction sites. So why don't we take this a stage further and think about using enzymes as our catalysts. Now, the good thing about enzymes, of course, is you're not running at even 100 centigrade, let alone 200 or 300 centigrade. Sorry. They're low temperature catalysts. The trouble is, though, they generally don't produce the products or mediate the reactions that we want. But there again, there's many enzymes that actually haven't been discovered, but possibly there are ways that we could actually modify enzymes to do what we want. Okay, cytochrome P450 enzymes. Here is a selection of hydrocarbons that are oxidized by that natural enzyme, and okay, there's stuff here that we're interested in. So maybe, then there's more enzymes to discover. Maybe there's a way there. But let's look at maybe a more artificial approach where we actually make an enzyme, or rather organize the steric space, organize a reaction space sterically. So what we can actually do, because enzymes and SSHCs operate similarly, they control the space, they control the reaction volume, if you like, to do the reaction. So, again, the reference is on the slide, the next slide, or the previous slide. They imagined an enzyme that could catalyze a Diels-Alder reaction, like that. That was what their aim was. And the way they went about it is they actually tried a bit of Darwinism, I suppose, of punctuated mutation from some wild type organism, and this is their type method they used. They were able to produce a hybrid enzyme and were able to insert effectively make synthetic enzymes, because they were able to insert transition metal catalysts into the active sites of existing proteins. You can then immobilize those enzymes on nanoporous systems, and it sounds science fiction, doesn't it? Except that the vast majority of United States fructose production uses exactly this technique with glucose isomerase. 10 to the 9 kilograms per annum production. Equally, with biodiesel, we keep coming back to that. The same idea, we can encapsulate lipase enzyme transesterificase to To do transesterification on the glycerides or triglycerides with methanol to produce FAME. How does it look? Well, it looks like this. So your enzyme is effectively encapsulated in a mice cell. You can do that reasonably straightforwardly, and then you have basically a synthetic, effectively supported catalyst, heterogeneous catalyst, but supporting reactions that you might want to do. Okay, if you're interested in biocatalysts, plural, this is a useful list because it probably shows you pretty much where the field is going up until about 5 years ago. So definitely worth a look. Phase transfer catalysts. Now, these are a special type of catalyst and effectively what they do is they effectively act to move reagents or products from one phase to another. So very useful in formulation chemistry when typically you're looking to do reactions. You have an oil-water, either water in oil or oil in water base, and you're looking to do a reaction which maybe only takes place in the oil phase or the water phase. Phase transfer catalysts are very useful there. There's a very, very useful application between hydrophilic and lithophilic phases, so they can allow solid-solid reactions, crown ethers, polyglycoethers, or liquid-liquid quaternary ammonium salts. It's worth remembering, if you can get an ion into the organic phase, it becomes very reactive. Therefore, you have lower activation energies, higher reaction rates, and lower energy costs. Very high selectivity, very easy to separate because you've still got the organic water situation, and you're using less hazardous solvents. So again, it's all looking very green chemical. So it's quite ingenious really, but all you're doing is you're engineering the reaction space. Now you can look at this in Manahan, but let's give you a little bit of the history of this and where it's come from. Probably as far back as 1946, there was the first clear-cut use of a phase transfer catalyst. So you have this very polar compound in the aqueous phase, you have this in the organic phase, and you use triethylamine to do the reaction, and effectively your phase transfer catalyst is formed in situ between your triethylamine and your where's it gone? Your organic compound that allows the reaction to occur. It was a while later though before people, I think, really realised what was going on, and probably Makosa in '69, and here's another very nice example of a phase transfer reaction, actually worked out what the mechanism might be. 1971 was probably the clearest early statement. So effectively what you're doing is you're moving the reaction space from, for instance, an aqueous to an organic solvent or vice versa, and you're using a so-called phase transfer catalyst to affect that transfer. For that you need good leaving groups, so Y in this case might be an anion with high hydration energies, and you need bad leaving groups. So low hydration energies is a bit of a silver lining, but thiocyanate iodide. So that will determine what reactions you can do in what how far you can push this, basically. And I've given an example here: substitution reactions with alkyl halides. More in a mo. Of course, because this ticks so many of the green chemistry boxes, because you're reducing hazardous reagents and hazardous solvents, actually this has an extra bonus, if you like, because if the poison or the harmful ingredient is only active in one system, then you can separate it and recycle it, so you cut down the use of it. Again, another example using polycarbonates and phase transfer catalysts. This is actually an explanation of the previous mechanistic slide, equation slide. Effectively, you've got bisphenol A and phosgene. Phosgene is not something you really want hanging around everywhere, but actually it's in the organic phase, so it doesn't really come into contact with the aqueous phase, so actually makes it a very safe reaction, much safer than you might otherwise think, and it reduces the use of hazardous reagents. The other use of phase transfer reactions is something called the hyperbasic effect. It goes on really with thinking about carbon-carbon bond formation. Sodium hydroxide, you wouldn't think a dilute solution of sodium hydroxide would be able to form carbanions from organic compounds, but actually by the hyperbasic effect it can. It reacts at the interface, and then the equilibrium is shifted to the right and you get very high yields. Again, I'll let you walk through these examples. I don't want to be here forever, basically, because this lecture could go on and on. It's a very large field. Photocatalysts, usually semiconductors, activated by light to form holes and electrons, and then those holes can migrate to the surface where they become a very strong oxidizing agent. Common examples of the type of semiconductor you might want to use will be titanium dioxide. It's got a band gap, a gap between here and here, of about 3.2 electron volts, which is in the UV range. So clearly the amount of energy associated with the hole is very, very high, which means it's a very strong oxidizing agent. Yeah, strong oxidizing agents, yes, particularly useful in synthetic organic chemistry, not yet. It's a bit too energetic, it's a bit too powerful, but brilliant in wastewater cleanup and the like. Okay, leaving behind heterogeneous catalysts, and I think you've seen that more and more homogeneous type catalytic systems are being moved into the heterogeneous form, simply because of the advantages. Let's now deal with the homogeneous catalysts. So basically, mostly used specialty pharmaceuticals. Waste is an issue, separation is an issue. Typical examples of the type of catalyst: acids and bases in esterifications, hydrolyses, etc., etc. So maybe you think, well, a large amount of saltwater waste isn't that much of a problem. When you start putting transition metal catalysts into the mix, actually it does become much more of a problem, and the amount of waste and contaminated waste that you have to deal with becomes significant. An example might be Wilkinsons catalyst. So Wilkinsons catalyst works very much like many of the other transition metal catalysts. You have a ligand pH3P is a very common one, and what that does, they're very good electron donors, so they're going to form reasonably stable bonds, and also they give a nice steric control on the process. And typically with these rhodium catalysts, they're very complex. You end up with dead ends as well. So homogeneous catalysts, very powerful. This is an example of a particular general reaction. Really, really useful, really widely used for specialty products and pharmaceuticals, but a lot of waste. How are you going to get back your rhodium? Very expensive as well. So homogeneous catalysts, yes, lots of advantages. They haven't, there's obviously active work trying to get these homogeneous catalysts into a heterogeneous form, because these Wilkinsons catalysts are very powerful, very useful, but there is still a big but. Let's continue and think. We thought about Lewis acids a little while ago in a supported heterogeneous type of context. Now, if we think about what we know about Lewis acids, they're water sensitive, they're not recoverable. Yeah, same problem really that all the homogeneous catalysts have. So, what if you didn't have to, if you could do it in a way where you had a way to recover the Lewis acid so you don't waste it, that it was water stable, recoverable, recyclable. Now, the way here is for instance, lanthanum trifluoromethane sulfonates, the lanthanum triflates. These do allow this type of process to occur, aqueous. And I'll use lanthanum as an example. There are others there. Okay, so here we have a number of examples of these types of these reactions occurring in water. Now remember what I said in the earlier lecture talking about green chemistry, water-based chemistry, and these reactions, certainly they're water-based, very expensive rare earths though. Nonetheless, it shows you the range of chemistries, organic chemistries you can do, and stereo-specific organic chemistries that you can do in water. So the story is moving on rapidly here. You may remember that in the other slides I gave you some example of nickel and cobalt being used, much cheaper than these rare earth metals here. Okay, let's continue. Asymmetric catalysis. Now, most of the pharmaceutical world now lives in the enantiomeric context, so that pharmaceuticals are sold as single enantiomers. The reason being reasonably obvious, that actually the body has a particular, the human body and the human chemistry has a particular enantiomeric and chiral focus, and often one finds that drugs of one chirality work and other chiralities don't. So enantiomer control is really quite important. Now, there are two routes. One is chiral auxiliaries, which is where you basically have a reagent which is chiral and you waste it to make sure that you get your product in the right chiral form. The other is asymmetric catalysts. Now, not all the way home yet. There are a few exceptions, but most asymmetric catalysts do not yet produce the required 99% or 95% enantiomeric purity. But nonetheless, they are beginning to be used and beginning to be better used as the catalysts are improved. So typical reactions for which you might use asymmetric catalysts or chiral auxiliary, typical reactions you might want to use asymmetric catalysts, or chiral auxiliaries are being used and which work is proceeding, might be reduction of carbonyls, epoxidation, isomerization, Diels-Alder, hydrogenation of alkenes. These are mainline chemistries. These are not necessarily your pharmaceuticals. The aim is to get these catalysts into the bulk chemical industry. Okay, but here is a pharmaceutical example, and we're looking at a binat ruthenium catalyst, and it's a Noriori catalyst, and you can see it's being used here. No great heavy chemistry, but enantiomerically pure product using this ruthenium catalyst. Okay, later we're going to look at the applications of some of these catalysts to the environment and in cleanup. But in terms of the fundamental use of catalysts in green chemistry, I think probably we'll call it a day here. Okay, thanks for watching. Goodbye.